with a heavy tail degree distribution, no long edges in this long-range percolation model can remove the subcritical phase. In all cases, this critical edge density parameter is positive. So you might ask, is it possible at all for such a sparse geometric random graph to have no subcritical phase? So when you come from this angle, it's surprising that there is a relatively natural example, and this is the so-called scale-free percolation model that was introduced in 2018 by Dijven, van der Hofstad, and Hochimstra. And this model combines the long-range percolation model with weights. So every Poisson point has a weight Wx independently sampled from some distribution, and we connect 2 points x and y independently with probability 1 minus e to the minus, and in the case of the long-range percolation model, we had just constant over distance to the delta d, and now we have the product of the two weights divided by the distance to the power delta d. And this makes a big difference if the weights are heavy-tailed too. So we assume that this delta is bigger than 1. This is again for sparsity reasons, and that the weights are heavy-tailed with a tail parameter eta. So the probability that the weight's bigger than r is a constant times r to the minus eta for r sufficiently large. And if you do this, Dijven, van der Hofstad, and Hochimstra for the lattice case, and later for the analogous Poisson case, Deprez and Wüthrich, have shown that there is a percolation phase transition if delta times eta is bigger than 2. So there is a subcritical phase under this condition, but if this condition is not satisfied, there is no subcritical phase. So this model can have, for a certain parameter range, no subcritical phase. If you approach this from a different angle, this is a very unsurprising result.
What is beta here? What is beta?
Beta, oh yes, you can, oh yes, sorry, there is no beta. The beta should be here in front of the product. Sorry, yeah, I forgot that. When I saw the formula, I thought I put it in the W, but I didn't. Yeah, so there should be a beta there. Okay, thanks for the question. Yes, so why is this from another point of view an unsurprising result? If you don't come from the geometric random graphs and long-range percolation world, but when you come from scale-free graphs that are not spatially embedded, like configuration model and so on, then this is exactly the result that you would expect, because in this, it's not so easy to see directly, but this condition that whether delta eta is bigger than smaller or smaller than 2 just says whether the variance of the degree distribution is finite or not. Okay, so if the variance of the degree distribution is infinite, we don't have a subcritical phase in these non-spatial mean field scale-free graphs. If the variance is finite, we expect such a phase, and this comes from local. These graphs look locally like trees, and you want for the non-existence of a subcritical phase, you want a super exponentially growing tree. Okay, so this is somehow an example that's not quite so typical, because this is almost not spatial, right? This behaves like a non-spatial model here. But what we will see in this talk is that there are also models with genuine that are genuine spatial models where we cannot have a subcritical phase, or where there are regimes where there is a subcritical phase and regimes where there is not a subcritical phase. And in order to study this systematically, I now introduce a model that encompasses all the models that we've seen so far in one framework. So here is the framework. This is called we call this the weight-dependent random connection model. And the vertex set is a Poisson point process of unit intensity on Rd And additionally, every vertex, every Poisson point has a uniformly distributed mark on the unit interval 0, 1. Okay, so every point has two coordinates, xt, x is the position, and t is the mark. And the idea is that a small mark indicates a very powerful vertex, and a large mark a not so powerful vertex. And the marks can have in the different model different meanings. So we will have this Poisson Boolean type where we want to associate radii. These are negative powers of the marks here. Of the weights in the scale-free percolation model will also be negative powers of the mark. And we will also have preferential attachment type networks where the mark will play the role of the birth time of the vertex because these are dynamical models. Okay, these are the vertices. How do the edges come above? So we connect two vertices x and y by an edge independently, given the positions and marks, with a probability which is a function rho. This is a decreasing function rho of, on the one hand, the two marks, and on the other hand, the distance. And to make the formulations as dimension independent as possible, we raise the distance here to the power d. Okay, so the crucial thing here is this kernel, this function g of the two marks. For example, in the scale-free percolation model, this has this just depends on the product of the two marks. But actually, we are more interested in much more general ways of how to turn the two marks into a factor here. So this is a symmetric kernel. We say it's non-decreasing because the rho, which is here outside, is a decreasing or non-increasing integrable profile function, which gives out, as a result, a value between 0 and 1, which is the probability of the connection. And because this is decreasing, large distances will lead to small connection probabilities, as it should be. Okay, I'll give you the examples for the kernels in a minute. First, we observe that there is, with these two infinite dimensional parameters, there is some redundancy because we can multiply the argument of rho with some parameter lambda and multiply the g from the outside with 1 over lambda, and this will just cancel out. So without loss of generality, we can sort of standardize this so that the integral of rho of norm of x to the power d, which by the integrability assumption should be finite, is actually equal to 1. So this is no loss of generality. This is just sort of calibrating the g and the rho. And if this is done, the advantage is, and I'm not sure whether you can see it, I can't because I have my own picture in front of it. Just a second. Okay, now I'm gone. So, all right. So the advantage of this is that the degree distribution, this is an easy calculation, does not depend on the rho. So no matter what rho we choose, so the degree distribution, with this condition here, this integral being to 1, the degree distribution just depends on the g. And that allows us to do what I said in the motivation, so that the rho will just help us getting these extra long edges, like in the long range percolation model, the ones that are not correlated via possible joint end vertices, whereas the G will sort of tell us how these correlations come above for long edges that are correlated via their long range, via their end vertices. The case of the classical random connection model or long-range percolation is no dependence on the marks, so G equal to 1, and then we just have a decreasing function of the distance here. Okay. Right. So this is the model, and it all comes to life when we look at examples. Okay, so for the examples, the kernels G are all have one parameter gamma, which is a parameter, a number in the interval 0, 1, and G regulates sort of the degree distribution, and we're only interested in heavy tail degree distribution with a power law exponent tau, which is 1 plus 1 over gamma. So the parameter gamma in all our examples that now follow will play the same role, namely it will determine this power law exponent tau deterministically as 1 plus 1 over gamma. Okay, now the examples, the crucial thing. So the first kernel that we're interested in is the sum kernel, and here is the formula. And the idea of the sum kernel is that these s to the minus gamma over d up to a constant, these are the radii. Okay, if you put this g in there, and if you put rho, which is an indicator function, then this will be the Poisson Boolean model that I already discussed. Because then the g gives us the sum of the radii because of this plus, and divided by the distance, this should be bigger or equal 1. This means that the two balls with these radii intersect, and this gives us the hard Boolean model, or the Poisson Boolean model. But now we're interested in a softening of this model, where we connect the 2 points x and y if the sum of the radii divided by the distance is bigger than another random variable that depends on the two end vertices. And these are all independent random variables with a distribution function determined by this rho. Okay.
But Peter, the radii are not random here, right?
The radii are random, yes. Well, they're random because the marks S and T are random, right? They are. I sample them together with the Poisson process. So every point gets these marks, and then I turn these marks deterministically into radii. But the marks are random, so the radii are random there as well. So this is a generalization. So if capital X is equal to 1, this is the Poisson Boolean model, and this is a generalization, this soft model where we have this threshold as another random variable that depends on that we sample independently for each pair of Poisson points, and that allows us to have these extra long long edges there that can arise without the radii being actually big, namely if this capital X is small. Okay, so this is the sum kernel. We can also put in the min kernel, where we just take the minimum of S and T to the gamma divided by this beta. And the difference in the hard version of the model, we connect 2 points if the balls intersect. In the min kernel, we connect 2 points if the center of one ball lies in the other ball. That's a variant that's not very much different. What is very much different is the preferential attachment kernel, which has this odd form, namely that the maximum of S and T is raised to the power 1 minus gamma, and the minimum is raised to the power gamma. This also leads to the same heavy tail degree distribution with the same exponent here, and the interpretation here is that the marks S and T play the role of the birth times of the vertices, and then if you sort of redistribute the terms here, you see if T is the bigger of the two values, you see in the denominator T over S to the gamma, which is the asymptotic expected degree of a vertex born at time S looked at the time T. So this is something like T divided by the expected degree of the older vertex, and if you know a bit of preferential attachment kernel of preferential attachment, this is what you do with preferential attachment, except that you replace here the actual degree by the expected degree. But qualitatively, this gives you the behavior there. So this is another kernel that we're interested in, and the final kernel is the one that we see in the scale-free percolation model. Here, there you take S to the gamma, T to the gamma, so you take the product of the two. This just depends on the product of the two marks. So this is this will lead, as we will see, to quite different behavior. Okay, so there's of course a lot of other possibilities how you could choose a G, but these are natural choices. And our interest is primarily in the soft models, and that's reflected in the case that we look at profile functions rho that decay like x to the minus delta for some index delta bigger than 1. So the model has an infinite dimensional parameter structures with the G and the rho, but we're staying away from critical cases, and then we have dependence just on two parameters, namely the gamma, which via this formula determine the degree, the power law exponent, and the delta, which tells us the decay of this softening variable and sort of determines the likelihood of extra long edges that are not correlated via their end vertices. Okay, and now comes the main result, which is our first theorem obtained last year. So we look at this weight-dependent random connection model with either of the kernels that we're interested in, either preferential attachment, some kernel, or min kernel. So this includes these Boolean type models, soft Boolean models, or the preferential attachment kind models. And in all these cases, there is a regime where there is a subcritical phase and a regime where there is no subcritical phase. So if gamma is less than delta over delta plus 1, then there is a subcritical phase. And if gamma is bigger than delta over delta plus 1, there is no subcritical phase. So the interesting thing here is that you can, in order to have no subcritical phase, you need both. You need sufficiently large gamma, so a scale-free network with a pretty heavy-tailed degree distribution, but you also need a lot of spontaneous long edges reflected in small values of the delta. Only when they work together, you can have no subcritical phase. If you have a hard Boolean model, which would be delta equal to infinity, or a model where there is not enough of both these things, then you will have you're in this first regime and you have a subcritical phase. So only these two long-range effects together can destroy the subcritical phase. For comparison, I have the result that was already known for the product kernel, which is due to Deifen, Debretz, and Wüthrich, who've studied this. And there you have no dependence on this geometric parameter delta. You just have that when gamma is less than a half, you have a subcritical phase, and gamma is bigger than a half, then you have no subcritical phase, as I already mentioned. So this just depends on the degree distribution, not on the extra geometry. I've written here less or equal because this is not because I'm generally interested in criticality here, because you typically not if you have these infinite dimensional parameters. But when gamma is equal a half, then the product kernel and the preferential attachment kernel give you the same graph. If you just, there's a gamma and a 1 minus gamma, they're both in a half in this case, and then you're not, then you're bang in the middle of this first phase where you have a subcritical, of this first regime where you have a subcritical phase, and therefore as a byproduct, you see that in this case, you have beta C bigger than 0. Okay, so my focus is on our main result here on the theorem 1, but before I tell you something about the proof, I formulate a consequence of this theorem for preferential attachment networks. So far I've looked at this infinite dimensional, this infinite graph where I say, oh, it's created like a preferential attachment graph. But preferential attachment graphs are normally dynamical networks that are built successively. And this is indeed the Benjamini-Schramm limit of such a graph. And we get, with a bit of extra work, a result for the network situation as well. So let me just spend one slide on this on this network. So the network, by network, I mean a graph process. GT, T is a continuous time parameter, and the graphs all live on the torus, on the unit torus TD, so that the underlying space is fixed, and the graph grows by points coming in one by one. So at the time 0, we have neither vertices nor edges, and vertices arrive successively after exponential waiting times, or if you want, like a standard Poisson arrival process, and they're placed uniformly on the torus. And if a new vertex comes in and we have a graph GT minus, so if a vertex is born at time t, we have a graph GT minus. If this new vertex is placed at position x on the torus, it's connected to each existing vertex, which has a position y and a birth time s, independently with conditional probability, which is rho, which is again our profile function, applied to t, which is the time we're looking at, the distance of the 2 points on the torus, to the power d, which is the dimension of the torus, divided by beta times t over s to the gamma. And t over s to the gamma is the expected, or asymptotically, the expected degree of the vertex born at time s, looked at time t. This conditional probability is natural in the sense that this is more or less the only choice where you have, where not the spatial effect dominates the preferential attachment effect, or vice versa. And this scaling is chosen such that both spatial, so the dependence of the connection probability on the distance and the dependence on the degree or the expected degree is genuine and not that one, and sort of on the same scale. Because this is a sequence of finite graphs, we're interested in the question whether there is a giant component, or in other words, whether the largest connected component of these finite graphs has asymptotically a linear size. And the network is called robust if the percolated sequence, so this is the sequence where we destroy every edge independently with probability p, if this percolated sequence has a giant component for every removal probability which is not 1. Of course, if you have a removal probability 1, then you destroy all edges and nothing happens. But if you have a 99.9% removal probability, we call the graph is robust if it still has an asymptotically linear largest connected component. And from our main result, we derive the following corollary. So the network is robust if gamma is bigger than delta over delta plus 1, and not robust if gamma is less than delta over delta plus 1. Okay, so this is the same distinction as before. So again, so what you need, so delta is the decay exponent of the rho, and gamma is the exponent that occurs here in this for this degree. So they play the same role as in the Benjamini-Schramm weak limit of the graphs. Okay, so this is a corollary for people interested mainly in networks rather than graphs. And I just go back to our main result. So in the rest, in the last 15 minutes, I'm going to tell you about the proof of this theorem here. So the theorem that says that in these models, there are regimes depending on both gamma and delta, where we have a subcritical phase and where we don't have a subcritical phase. So we start with part B, where we do not have a subcritical phase.
Okay. Does the size of torus depend on T or it is fixed? What is the size of torus?
No. Good point. So the torus TD is a torus of unit size. It doesn't change. It's a fixed torus, and we have more and more points coming in. However, the probability, that's why this factor T is here, the probability of making connections decreases in line with the number of available older nodes there, so that we still have a sparse graph at every time T.
Thank you.
Sorry, I have a question.
Yes.
What do you mean by asymptotically linear size?
Okay, so you look at the at the number of vertices in the largest connected component. You divide it by T, and if you want the lim-inf of that is positive, but in these models the limit always exists, so the limit is positive. Limit of the number of vertices in the largest connected component divided by the number of vertices, which is asymptotically T, because this is just a Poisson process, is positive.
Okay, thanks.
But of course, it's positive, but the proportion is getting very small if you remove a lot of edges. That's clear. Okay. Further, it's a good time for questions before I start proving things or giving you a hint of the proof. So if not, okay. So, okay, right. So I've singled out the preferential attachment, the sum, and the min kernel as particularly interesting. But there is some order between them, and for the non-existence of the subcritical phase, it's enough to work with the largest kernel because this has the fewest number of edges. Okay, and few edges make it difficult to have connectivity for all beta. So it's enough to work with G-min, and one of the results, of course, is this holds for general kernels G that are less or equal constant times G-min kernel. So G-min is the kernel beta inverse times the minimum of S and T to the gamma. Okay. What's crucial for the existence of an infinite component that cannot be destroyed by reducing the edge intensity or by percolation, if you want, is that this has to go to vertices of increasingly large degree, and these vertices exist, of course, in our model. There are vertices of arbitrarily large degree. The question is just how close are there, and do we manage to get there? And for this part of the proof, it's constructive. We have to construct a way how to get to these vertices of very large degree. And here is what's not so hard to prove. If you start already with a fixed vertex x0, s0, so this is a vertex in position x0, the position doesn't play a big role, with mark s0, which is already small, the probability that there exists an infinite sequence of vertices such that the next vertex has a significantly smaller mark and therefore a significantly larger degree, in the sense that the mark of the next vertex is smaller than the previous mark to the power alpha 1, where alpha 1 is a number bigger than 1. And then, and this graph must also not be too far away. Okay, so this is the sequence of vertices of increasingly high degree, and they are connected not directly, but by a path of length 2. So the vertex xk sk is connected to xk plus 1. These are very special vertices with very high degree, and they're not directly connected, but they are connected via one other vertex. And this other vertex is not a special vertex. This is a vertex with typically low degree. The fact that it exists comes from the fact that these two vertices have so high degree that the chance is good that they are connected to a vertex not too far away. That is an ordinary vertex connected to both of them. Now, this is a good strategy for these kernels, because if you look at these kernels, and if you have, if you think of these as a sum kernel, for example, and you think in terms of radii, if you want to connect 2 points, if one has a very large radius, that the other one also has a very large radius is not particularly useful. It's enough to have just one, if the effect just comes from one radius being very large, that the other radius is also large is no longer very useful for you. Okay, and therefore it's a better strategy to have one large radius, possibly being connected to a lot of normal vertices, because these vertices don't need a very large radius. You just need a lot of them so that you get so that you have a big choice for these vertices to be connected to another vertex with an even larger radius. And there you can also see that this strategy can only be successful if you have a soft Boolean model rather than a hard one, because if you have a hard one, you cannot extend the choice of sort of connecting vertices very much. You're still bound to be in this local area, whereas the softening gives you extra potential to find these connecting vertices. So this strategy, it's not hard to calculate, works if and only if gamma is bigger than delta over delta plus 1. Okay, and the product kernel, you can see, is quite different, because for the product kernel, it is useful if both radii or both weights are they're very large. So because they're multiplied and not added, or the min or the max formed. Okay, so this is the constructive and therefore easier part of the proof. What's harder to prove is the part where you have to show the existence of the subcritical phase, and therefore sort of that there's no such strategy that allows you to build large connected components, whatever the edge density. And there we have to work with the smallest kernel, and this is in this case for us the preferential attachment kernel. Okay, so the first idea in the proof would be to do a first moment bound. You look at the expected number of self-avoiding paths of length n starting in 0. And we've slightly strengthened the notion of being self-avoiding by saying shortcut-free. So self-avoiding would mean that a vertex is not revisited by the path, and shortcut-free means that the neighbors of a vertex are not revisited after the first step. So there is no shortcut, there is no edge that connects 2 points in the path that are further than 2 steps away from each other. So you would hope that you can just count these number of paths, and if this count gives you a constant times beta to the power n, Then you can choose your beta less than 1 over c and use Borel-Cantelli, and then you've shown that there are no infinite paths and therefore no infinite connected components. This strategy works only if gamma is less than a half. Okay, if gamma is bigger than a half, we still want to show existence of a subcritical phase, because we want to, this regime should reach until delta over delta plus 1, which is significant, can be significantly bigger than a half, and then this strategy doesn't work. And the reason why this strategy doesn't work is because this expectation is dominated by paths that use vertices with extremely small mark and therefore very, very large degree. And these have so large degree that there are many paths going through them, and that dominates the expectation. However, if you start in 0, you never reach these vertices. They only appear in the expectation, mess up the expectation. But if you look at the almost sure picture of the paths, or the pathwise picture, these you don't reach these vertices, and therefore you need to do something else. The crucial thing in this is how do you reach vertices with a low mark? And in order to do this, we look at our path and identify the skeleton, which is sort of the path of the path that's used to go to vertices with small mark. And we get the skeleton by success. Okay, maybe I should explain this picture. On this axis here, we have the marks. So this is the interval 0, 1. And on the other axis, you just look at consecutively at the points of a path. Okay. And then you successively remove the local maxima from the paths until you arrive at a path that goes to lower marks, and then from the lowest point goes up to higher marks. And so that's exactly the paths that have no more local maxima. Okay. And we want to, the skeleton tells us how the path goes to the vertices of high degree or of low mark. Okay. What we need is, when we have the skeleton, we need to bound on the number of paths that could connect two consecutive points in the skeleton. And this is our crucial tool in the proof. So we look at the set of all shortcut-free paths connecting x and y by k-1 vertices, or k edges, that all have larger marks. Okay, so because they're in the skeleton, if you're in the skeleton, the path connecting these two consecutive points of the skeleton, for example, this one and this one, if you see my cursor, these are vertices with larger mark. Okay, and our crucial tool is that the expectation of the number of shortcut-free paths that connect 2 points x and y via k-1 vertices with larger marks is bounded by constant times beta to the k-1. This is the kind of term we're craving for the first moment method, times the probability that x is connected to y, which is a term we need in order to deal with all the possible skeletons later. So this is what you have to prove, and the problem in this proof is the combinatorics of the paths of these paths of length k. There can be a lot of different paths of length k, and we sort of need to classify them in order to use the estimates. We classify them by binary trees. So if you have this these 2 points, then you look at the marks of the vertices, connecting them, these k-1 vertices, and you start with the lowest mark, which will be the root of your binary tree, and then you look whether the next lowest mark is to the left or to the right, and that tells you whether the child, you have a left, the next child is to the left or to the right in the binary tree, and so on. And so you encode where you have to insert your local maxima by a binary tree. And because the number of binary trees grows like at most 4 to the k, we can hide this here in this c to the k-1 here in this term here. Okay, and when we have this way how to insert the local maxima, we have the key calculation is, and again I have my own picture in front of. Okay, so the key calculation is when you insert one local maximum between 2 points y0 t0 y1 t1, you insert 1 point, you look at the expected number of possibilities how you can insert one local maximum, and then a calculation tells you that this is like less or equal a constant times beta times the probability that the two endpoints are connected. And this is a calculation that only works if gamma is less than delta over delta plus 1. If this is not satisfied, you just get you can still calculate this double integral, of course, but you get another right-hand side, and this would not allow you to get this useful tool here. Okay. So this useful tool allows us to count the number of ways how you can get from one point of the skeleton to the next one. And from then on, it's sort of everything will be fine because we have this powerful tool. We now use on the skeletons the truncated first moment methods. So you still on the skeleton, of course, you have to make sure you can't just do the first moment method because it would still, the expectation would still be dominated by paths that go to so low marks or so small marks that they actually don't exist. But you can deal with this now by a truncation. So you take the look at the skeleton, and it's fine or regular if its lowest mark is larger than 2 to the minus m. So the skeleton is regular if the lowest mark is larger than 2 to the minus m, where m is the length of the skeleton, and the path is regular if the skeleton is regular. And an infinite path is regular if all paths from a certain length on are regular. And then you can deal with the irregular paths by stopping when you go below the threshold, and use the tool to show that this actually doesn't happen, and every infinite and that every infinite path is regular. And then you estimate the regular paths where you now have a lower bound on the mark. By constant times beta to the n. That was the original plan. Now we do it on the skeleton rather than the original path. And if beta is less than 1 over c, there are no infinite regular paths, and every infinite path is regular. So there are no infinite paths, and therefore you're in the, for the sufficiently small beta, you're in the subcritical regime. Okay, so this is the idea of the proof, and if I have time, let's see, 2 minutes, I have one last slide telling you what else we're doing in the group, further interesting topics. So what else are we working on? So there's one thing that's very close to completion, will appear on the archive in 3 weeks' time. So there we look at typical distances of vertices in the infinite cluster in these weight-dependent random connection models. And again, there's a qualitative change in the behavior depending on whether gamma is bigger or smaller than delta over delta plus 1. If gamma is bigger than delta over delta plus 1, we have a limit theorem for the distance of two points x and y at large distance in RD, namely the distance is 4 log, so it's ultra small, log of the Euclidean distance times a constant that depends just on gamma and delta. And if gamma is less than delta over delta plus 1, it's of strictly larger order. In fact, we get a lower bound.
Sorry, what are x and y?
X and y are 2 points in your Poisson process. You can add them to the Poisson process, for example.
What is the typical distance?
The typical
Graph distance?
Sorry? Yes,
this
graph
graph
distance. Yes. This is the graph distance. So you put 2 points x and y at Euclidean distance x minus y. This is this term here, and then you ask what's the graph distance, and the graph distance is constant times log of the Euclidean distance. The constant is explicit here, and that holds asymptotically as the distance of the points, the Euclidean distance of the points goes to infinity, and their marks should be unchanged, right? You can't simultaneously change let the marks go to 0. Okay, right. And what's crucial is that this change of behavior occurs again when gamma is delta over delta plus 1, which is not what you expect when you're coming from the non-spatial graph or network world, where there you would expect this change of behavior when the power law exponent is 3, which would be gamma equals a half in our setup, but it actually depends on this delta here too. So this is all essentially finished project with Peter Grazer and Arne Grauer. We look at further properties of this infinite cluster here, for example, recurrence and transience of random walks on the cluster, which is an ongoing project with Peter Grazer, Markus Heidenreich, and Christian Mönch. And in a project which is funded, but still in its infancy, with Arne Grauer and Amitai Linker, we'll look at the spread of infections on these graphs. And long-term plan with Peter Grazer and Amitai Linker is also to use the fact that we have spatially embedded graphs to let the points move around. So to look at time-varying graphs or networks. But this is still in its infancy. These are the next plans for the research on these spatial random graphs in our group. Okay, so thank you very much for your attention.
Thank you very much, Peter, for this lovely talk. So we have time for a few questions, maybe. So are there any questions in addition to those we already had?
So I have a question. So have you considered also the case where points are Poisson? You have a Poisson point process on RT, and then you mark points with a generic distribution. So the marks are IID, but with a generic distribution.
So what we look at, of course, is in order to fit all these models into one framework, we give a uniform distribution, but then, of course, the kernel G tells us to do something with the uniform distribution, and we want to turn the uniform distribution into a heavy-tailed distribution by raising the variable to the power minus gamma. So, so the interesting regime is when this is heavy-tailed, and instead of taking just s to the minus gamma, you could also use a regularly varying function there. So this would be pretty generic distribution. We haven't done this, but I have no doubt that this would be possible. because I mean we're looking at results that are away from the critical value, and therefore you expect the universality for this. This, of course, would wouldn't expect this if you're if we had results for gamma equal delta over delta plus 1, then this is. But because we are in away from this transition here, yes, I think that would translate to a result for a generic distribution of the monk.
Thanks.
Any other questions, maybe?
So what happens if gamma is equal in theorem 3? Can both happen, or?
I would expect this, yes. The reason why I never say anything, and probably we could even get this if you look at the proofs, but the problem is that in reality you have infinite dimensional parameters, right? You have this rho and this G, if you're at this critical value, then really, I mean, so all the rhos and G's that correspond to gamma and delta, if you have strictly less or strictly bigger there, should behave the same way. But if you have gamma equal delta over delta plus 1, then suddenly you make very special choices that will probably have an effect on the result. So if you work much harder, maybe you can get a result that tells us where exactly the transition is if gamma equals delta over delta plus 1, but it would depend on rho and G, right? And not all the rhos and G that correspond to the same gamma and delta would have the same behavior, I would think.
I see.
What is a percolated sequence in the definition of robustness?
The
percolated sequence. Here, yes. It is robust if the percolated sequence.
Okay. So this is the sequence of percolated graphs, right? So you take the graph sequence that you start the graph process here, this GT. Okay, the word sequence is bad because it's actually a continuous parameter. Sorry about that. So you take this GT and then you percolate it by independently removing every edge with probability P, and then you have a family, not sequence, of graphs GTP. And robustness means that for every removal probability P less than 1, this family of graphs, the largest components in this family of graphs is asymptotically linear.
Thank you.
Yeah, sorry. This is very imprecise here. The word sequence should be family.
Okay, so thank you very much, Peter. I think we're running late already a bit, so I suggest that we all unmute ourselves to thank Peter for his talk.
Thank you.
And maybe we can have just a 1 or 2 minute pause before we start the next talk, if that's all right, Nina?
Yeah, let's do that.
Okay, so
let's have a 2-minute break.
2-minute breaks, and then we start again.
Markus, du kannst ja schon mal den Bildschirm teilen.
I try.
Ja. Okay, let's reconvene. Welcome back, everybody. Our second speaker is Markus Heidenreich, and he will tell us about the percolation phase transition in random connection models, about the critical behavior for weight-independent models. Markus, the screen is yours.
Thank you very much. And yeah, I'm very thankful for this invitation to give this talk today. This talk will be a continuation of the previous talk in the sense that it's about the random connection model, and it's also a continuation in the sense that it's about the percolation phase transition, but it's a discontinuation because we'll interpret the term transition differently now. And in a way, this will be, the model is a little easier than the previous one because we kick out the weights and we just have the points, so the locations. Before we start, I should say that this is based on a joint work with Remke van der Hofstad in Eindhoven and Günther Lass from Karlsruhe and a PhD student from Munich, Kilian Matzke, who is nowadays a consultant. So a short, I don't know, maybe recap is not really necessary, but somehow I thought it's nevertheless good to say what's the object that we're studying, the random connection model, and somehow you should think of that as being now weight independent in the sense that the weight is gone. And then this could be viewed as a continuum version of long range percolation, if you like, or continuum percolation model. So we have this function phi, it's the same function phi as before. I think in Peter's talk somehow the argument of phi was only the distance between. Now you put in really the difference between 2 points in RD, which is again in RD, and so out comes a number between 0 and 1, and we want to use this probability, this outcome of phi as a probability that we put an edge between two edges. We make some very convenient assumptions about this function phi, namely this rotational variance. So somehow it doesn't matter whether the points are like this or like this, only the difference, say the Euclidean difference between these two Euclidean norm counts. And also that it's decreasing in norm. So the further the points are away, the more difficult it is for them to connect. The Poisson point process, I've kind of used notation eta. It should have an intensity now, and this time we want to play with the intensity. So in a way, the intensity has a similar character as the beta in the previous talk, but somehow think of lambda small, meaning like very few points, and lambda large, there are lots of points. Good, and maybe I should, I would like to make a few comments on that somehow in order to be a little more formal. So this random connection model you can see as a pair of eta. Eta is now the realization of the point process with the intensity lambda say, and then for each pair of vertices there is an extra random variable, and this one you could think of being a uniform random variable which you use in order to decide whether or not there is an edge between these 2 points. So somehow say this uniform random variable, if that is smaller than this function phi of the difference between the 2 points, then we put the edge there, otherwise we don't put it. And then of course you can play with the phi and use different phis, and then for different phis you get different models. The first one is a Boolean model, a Boolean in the sense that this function phi takes all these values 1s and 0. So since we want this function to be decreasing, it means that it's first 1 for a while and then afterwards it's only 0. And in that sense, we come back to the Gilbert disk model, which was already studied in the 60s. And you can, if 2r is this point where it's jumping from 1 to 0, then we can kind of interpret that as 2 points are connected if they are closer than 2r. Whenever they are closer than 2r, then we make an edge in between these 2 points. So that's what I've simulated here. So these are the realization of Poisson process, and then I've put a disk of radius r around each point, and whenever 2 disks overlap, I make an edge between these 2 points, and somehow on the right-hand side you see a realization of this random connection model where precisely when you see here that a few points overlap each other, and then you see somehow here the corresponding edges, for example. So it's really the same realization. Another example that would correspond somehow to the choice of this function rho in the previous talk also would be a long-range model where these things go, this function phi goes down, goes to 0 in a much like softer way, and it's heavy-tailed, so there's a binomial distribution here. So let's say that this phi of x is 1 over norm to the d plus alpha. So the d will soon come because we want this to be integrable, so that's why we need the d, and then there's a little bit, and a little bit we can play with. You may view this as a parameter, and of course this should not be larger than 1, so we have to make a cutoff here, so otherwise it would not be well, we cannot interpret this as a probability, and then we put in a parameter L, which we can think of being a very large number, but a large but finite number, which is there for technical reasons, and we come to that later. So these are two concrete examples that you might want to think about. Now comes to the transition that I want to study, namely the transition when we vary the intensity of the Poisson process. On the left-hand side, we see a small density Poisson process. On the right-hand side, there's large or high intensity. And you see somehow if there are lots of points, then the distances are not so large, and therefore you will have much more edges because somehow it's very easy to bridge the gaps. Whereas on the left-hand side, so points are typically, we see when they are kind of close and there's an edge, but if they are like a little too far, then it's somehow there you don't have any edges. And then, as usual, I mean, you play with the parameter lambda, and so for small lambda there's no infinite cluster, for large there is, and then lambda c is a critical lambda, and this is a transition now. It's a transition in lambda that I'm interested in. So we vary only the intensity of the Poisson process, and this is somehow the infimum of all those lambdas where an infinite connector component exists. So let me answer the question from the previous talk, namely whether there is always, or whether this lambda c is trivial or not. And so that was, as almost always, was also kind of already mentioned in this particular case, was already studied by Matthew Penrose in 1991, who showed that there is really a phase transition in the sense that this is not, so it's neither 0 nor infinity. If and only if, so that's even stronger than quoted here, if that function phi is integrable, if this one can be, has a finite, otherwise, so if that is infinite, then lambda c is equal to 0. Okay, and so the point I want to make is what happens at and close to lambda c. Can we say something about the model around this phase transition? So the object of interest, or I mean, what should we look at, is a so-called 2-point function. So we take 2 points, put them into space, and then we ask whether they are connected. Well, one problem which always arises when you study this, make these continuum models with Poisson processes, you never know where the Poisson points are because they're random. And so in order to study them, we want to ideally want to have points that we can hold on. So like fixed point, say the origin, and like another point. So, and there are different ways to deal with that. And so the most convenient way here is certainly, since we have the Poisson cases, to look at some kind of Poisson version, so that you take an augmented Poisson process. You take your realization of a Poisson process and you add 2 points. So let's so in this picture down here, let's say the black points are all the Poisson points, the random points. And so what we do now is we add points here. Say maybe there's a point here. Say this is X, and then there's another point here, which is maybe Y. And then what we do is we kind of take these 2 new points, X and Y, and so somehow between the Poisson points there are already edges, so these are already sampled, but so the new points, they don't have edges yet. So what we do is with all the available Poisson points, we kind of test them, and we add edges again with the probability depending on the distance between the point X, say, and this Poisson points. So let's suppose we do this here, and then we get some point, this one and this one, say, and maybe this one is connected here, and here. Yeah? So these are like new edges. So X and Y are fixed points in RD, but all the black points, these are the Poisson points. Yeah? So that's to clarify this notation. Xi, xy. Again, xi was the realization of the Poisson of the random connection model, so it's a Poisson point and the edges, and the xi xy is somehow the same thing with the 2 extra points added. Okay, so that gives us a function. It's a real function, so it's really like RD times RD as an input, and has 0, 1 takes values in 0, 1, and this is a function that we want to study. And so this function is one way to characterize this phase transition. So when we are in the so-called below lambda c, then we are in so-called subcritical phase. Clusters are finite, and they're not only finite, but also the clusters have an exponential tail. So clusters are connected component exponential tail. Well, one way to measure sizes would be like to count the number of vertices, and so having exponential tail means somehow the size is larger k decreases like e to the minus some constant times k, and the constant of course depends on lambda. Yeah, so that is really strong, and that was already proven in the 90s by Meister, and like many results in the 90s, it was the technique was to discretize and then use techniques from the lattice case and carry them over to the continuum and take limits. So that was Meister's proof strategy. For the supercritical case, so when we are above lambda c, then this function tau lambda is uniformly bounded from below. So normally we look at the function when the distance between x and y kind of increases and the 2 points are going further away, and then we study, well, how's tau behaving? And in this case, it's not going to 0 at all. Why not? Because there is a unique infinite cluster, and there's a certain chance somehow that you'll find in your neighborhood at least one vertex of the infinite cluster, and then you only need to connect to the, well, if both x and y need to connect to this infinite cluster, and it's unique, so therefore this already is enough for them, these two, to be connected. And then the question to be addressed now is, what can we say something about this critical regime? So what happens really at this lambda c? And the answer comes now. And so here's, yeah, well, our theorem, and it's not so, it does not appear so inviting at first glance, maybe, but it is a powerful result, and I would like to convince you of the fact that there is a certain beauty in it. And so let's look at this regime first. So we have these two regimes. Either this phi, there are some very soft assumptions, so I summarize them under well behaved, and the dimension is sufficiently large. So I can't really tell you how large, it also depends on phi, but somehow you should read this as there is a dimension d0, which is at least 6, such that for all d dimension larger than this d0, the following is true. Yeah, this is what therefore I call this a high dimensional case. So I mean, this d0 is implicit. Well, it's not computed, but it's computable. The second regime is particular for this so-called long-range case. Somehow, when this phi had this special binomial tail, which I was saying earlier, then it is enough to be in dimension d larger 3, and then there's a minimum of alpha and 2. It's this alpha here. So somehow, the smaller the alpha, the e is the smaller the dimension we can take. Yeah, somehow small alpha, and but so something has to be large, and so that something can, for example, be this parameter. So this thing of that again as a high number, it has to be sufficiently large, but then the following is true. So what is the following? It is here. There is a uniform constant. Think of like 2, for example. And then on the left-hand side, there is the 2-point function, but not the 2-point function itself. It's a Fourier transform. So it's called, this bound, which in this red box is called an infrared bound, because it's in Fourier space, and it's most interesting for case being close to 0. Yeah? So the case close to 0 are the ones that give us the relevant information, because they correspond to the spatial distance between the 2 points being large. And this is what we are interested in. We kind of want to see the asymptotics when x goes large, and that would kind of correspond to k going to 0. It's true for all k, but for k close to 0, it's most interesting. And this is bounded from above by this constant over, and here we have, again, the Fourier transform of the function phi. Again, phi was the probability that 2 points are directly connected, and tau was the probability that there is a path starting in one of the points, going over like some intermediate points and ending at the other point. So the function tau is a complicated function because, well, this is really the 2-point function where we have the path. Whereas the function phi, that is an easy function. We are given that function and we just can compute the Fourier transform. So this is the easy part, whereas somehow this is the thing that we want to that we really need to understand. So this gives us, therefore, it bounds a complicated quantity with a simple quantity. So for like generally when k goes to 0 under some moment assumption, this phi hat of 0, so the denominator behaves for k close to 0 as norm k to the square. And in the second case, it depends a bit on the alpha. If the alpha is larger than 2, then it's also norm k to 2. But otherwise, it's norm k to the alpha. Yeah, so there's this 2 minimum alpha here whenever there's an alpha. And otherwise, it's just 2 in the exponent. So that's the main thing to think about this one. So, and this is true for which lambda? It's true for all the lambdas which are smaller than lambda c uniformly. Yeah? So this, in particular, this constant here does not depend on lambda. Well, okay, so what can we do with this infrared bound? Well, it has a number of consequences, and the consequences give the meat. So first of all, there is a so-called triangle condition. So the triangle condition has a certain reputation in percolation theory, particularly high-dimensional percolation, as being a sufficient criterion for a number of nice properties. And so what's a triangle condition? Well, here's a continuous analog, but it's, well, some people that know percolation good, they will see similarities with that. So that's a quantity. We write this triangle sign. So if this is defined as the threefold convolution of this function's tau. So you can think of that as saying there's one point here and there's another point here and another point here. Let's say this is 0, x, and y, and then we take the probability that there is a path from 0 to x times the 2-point function from 0 to y and the 2-point function from y to x. And then you integrate this over x and y. That's the convolution which is written above there. Yeah? So this is a quantity, and the triangle condition means that this triangle diagram is finite, and indeed it is under these assumptions here, so namely when this is true, because this triangle diagram we can rewrite in Fourier space, and the convolution becomes a power in Fourier space. That's one of the reasons why Fourier space is often good when analyzing convolutions. And then we can plug in this bound here, and we bound this from above by this constant over this, and for this we put in, say, norm k to the minimum alpha. This is getting power 3. It's like 6 minimum, or 3 times the minimum of alpha and 2, and this is finite in dimension d greater 3 minimum alpha. And you see somehow that there's no surprise that somehow this is playing a role here. So that is finite. So this in particular means that there's no infinite cluster at criticality. That's one of these questions about percolative systems in general. If you are at the critical point, is there an infinite cluster or not? And here we already see it's not, because if there was one, that would mean that tau would not go to 0, and that would mean that this could never be finite. There are further consequences, namely so-called critical exponents. So they come, yeah, more or less, not so directly, but they come out of this trying condition. So once we have this trying condition, then we can derive from that also that, for example, here's one example of this. If we look at the expected size of a cluster, so the expected number of vertices in a fixed cluster, and we look at that for lambda, which is strictly smaller than the critical lambda, but then we let lambda go to lambda c. So that's what sometimes called a near critical behavior. So we approach lambda c from below, and then this is diverging. It's diverging to infinity, and so we get a very precise description of how this diverges, namely 1 over the distance between the lambda and the critical lambda as we are approaching this. And out of this, we also get an asymptotic for the critical point for lambda c when the dimension is going to infinity. So that's one way to view this model is that you can think of like it's one model per dimension, and then you let the dimension go to infinity, and then you say, I mean, how's this dimension? I mean, how can you say something about lambda c as d goes to infinity? And indeed, that is possible, and so it's basically 1 over, and then this is integral over phi. So this, the limit already was identified also in the 90s by Meister, Kernels, and Zakar.
Probably d in -1 fourth, d in the power.
Yes, thank you very much. You're very right. Well, the good thing is with these handwritten things, you can immediately correct. Yes. Precisely, of course, it's otherwise it would be useless. Yeah. Indeed. So I already hinted that where is this inspiration coming from? So there's one slide about the origins of this theory. So it's coming from percolation on lattices. So on lattices is partially well known, partially somewhat newer, this whole proof, which I'm sketching at least some aspects of now, has like 2 sources. So one is somehow this percolation on lattice thing. So I mean, you need to know your percolation theory, and the other thing is the point process theory. So really like special properties of boson processes, which you bring together in order to get this description. So here's one slide about percolation on lattices, and there is a method called the lace expansion, which has been pioneered in a seminal paper by Takashi Hara and Gordon Slate in 1990. And that was really very influential because somehow the method they developed turned out to be very, very fruitful, and that's also like the main method here. So they proved also an infrared bound, and you see somehow that at least the way it's written here, it looks very, very much, very, very similar to the previous slide. And then, I mean, people investigated, I mean, how to optimize the dimension. So somehow they also have that D has to be sufficiently large, but at least 6. And then, I mean, how large? And then there have been numbers floating around, but somehow the best, after a number of more optimizations, so D greater or equal than 11 is the number that came out in the work of Fitzner and Hofstad 3 years ago. So this has also been done on site percolation. On site percolation, somehow the randomness is on the site. So you put on sites, sites are occupied or vacant, and then you call things connected if somehow you go from like this blue stuff would be a cluster or a connected component. So like, but somehow there's no connection from here to here, and then you can also prove such a infrared bound, but somehow there are a number of technical problems, so that is much more recent, and it has also been done for long range percolation. I should say maybe that somehow in general, I mean, saying something about critical percolation is like a big question. Of course, there are like there's enormous progress on the planar case on 2 dimensions, because then there are like fantastic tools like particularly planarity, duality, and these kind of things. And in high dimensions, you have this method of lace expansion, but these are the two main tools to do things. And otherwise, I mean, there's a big gap in the theory. And I should also maybe mention only briefly that for long-range percolation, at least, there is some recent progress by Tom Hutchcroft with completely different methods, even though they are not that completely different. So certain ideas which now follow, like Bootstrap Arguments, are also instrumental in his work. But that's really very recent, but it's not quite optimal yet. But at least this is for all dimensions. So strategy for us is now to adapt this lace expansion for the Poisson case and to do things in continuum, and in particular deal with these special effects of point processes. Yeah, so I would like to say something about this theory now. First, more a general overview, what's the basic strategy, what are the key ideas, and then I would like to focus on one of the first parts, because there it's really like the most novelty, and then give some concluding remarks. So this lace expansion proof has 3 steps. Yeah, maybe before I say something what the steps are. So one question that often appears is, why is it called lace expansion, and where are the laces? And the answer is they will not come, because this lace expansion for percolation has its root in a lace expansion for a different model that was devised by Spencer and Bridges in 1985, and there they use class of graphs which they call laces, but somehow for the percolation these graphs have no use, and there's an inclusion-exclusion expansion. But somehow for historical reasons the name has stuck, and so we still call it lace expansion even though there are no laces. So we want to derive an expansion of the 2-point function. It's an expansion of the following form. The tau xy, you remember that was a 2-point function. That's a probability that 2 points x and y are connected via path, is given either as a sum of a number of objects. The first thing is phi of xy. Phi of xy means there's a direct edge between the 2 points. That's always possible. Or this pi, there's a quantity called pi. That will soon say something, and then there's a convolution of the function phi again, which is a 1-step thing, and then there's a plus this mysterious pi with the function tau. Somehow it is phi plus pi, and then there's a function tau, and somehow you can really interpret that convolution spatially. Somehow you go somewhere to intermediate point z, and then from z to the destination y. So in short, this is somehow this function. Identities of this type are known in the physics literature as Ornstein-Zernike equation, and physicists can analyze this with non-rigorous but with exact methods. In the physics literature, this quantity pi is called direct connectedness function, which is a bit misleading here because direct connections are by the phi and the pi are not the direct connections, but somehow this is a terminology which was originated in different models and which comes here together in a somewhat unfortunate way. And yeah, we often call it just lace expansion coefficients, and this pi is kind of identified as part of the expansion. And then there's an observation, namely that this expansion resembles a completely different model with a very similar expansion. And that model is a random walk on the augmented Poisson process. So again, eta was a Poisson process and eta xy was a Poisson process with the added point at x and y. And then we have some version of the Green's function. So this we should interpret as somehow it's a random walk. It's a probability that a random walk starting in x, jumping on this Poisson process comes in n step to y, and we sum this over n. So it's like a version of the Green's function, and it satisfies the following equation. Somehow this Green's function is somehow this is like the case that we have make only 0 steps. So I see there's that should be a 0. Sorry, no 1 is good. No, sorry, that was. I apologize. So you directly go to the goal in one step, and then that's over. And otherwise, that you make you jump to one other point, z, and then from z somehow you go to y in a -1 step. But somehow, since you sum up over n, we have this identity. And now compare the two green identities. So one which is already green and this one.
So
and you
Marcus,
see that
when you say random walk, you mean that you go to the closest points, or you can jump everywhere?
That's a yeah. I've been a bit vague here by purpose, because it's what we do. What we actually do is not quite this, because we really look at the convoluted measure and sum this up. But the best to think is somehow that you have only the points, and then you choose your neighbors with according to the distance, and you kind of have a weighted model, in the sense you divide by the sum over the phi's between the point and all other possible points.
I see.
You use phi xy as a weight.
Mm-hmm.
Yeah, the two green lines are almost the same, except the pi. Yeah, so this capital pi's. So if you would remove the capital pi's in the top green line, then it's the same as in the second green line. And this is the guiding thread for the whole analysis, that you hope that somehow the capital pi's are small. They are actually so small that the two quantities are somewhat similar at least on the level of the exponents. And that is what this proof finally achieves. So once you've identified the expansion, somehow now you want to show that somehow the pi is small. And how are you doing this? So you first have, well, once you've identified the pi, you need to bound the pi's. For that, we have a BK inequality named after Vandenberg and Kesten for increasing events for the random connection model. Of course, there are already a number of BK inequalities for Poisson processes, which we're also relying on, but it's not enough somehow to take only a BK inequality for Poisson processes, because you have the edges. I mean, well, maybe for the non-experts. So BK inequality, what does it say? It say if you have two increasing events, and increasing events are those events that the more edges you have, the better. For example, that you have a connection from here to here. This is an increasing event, because the more edges there are, the better for the connection to be established. And so now you want to have the disjoint occurrence of such. Disjoint means that for one path you use some edges, but these edges you cannot use for the other event. Yeah, so somehow you have all the edges that kind of are helpful for your events, but you have to split up the edges that you have, and you can only use like some for the one event and some for the others. And this disjoint occurrence of two events is bounded, is negatively correlated, so it's bound from above by the product of this. And so, but there are some technical issues, but somehow it's possible to deal with them. Maybe that's enough. The pi is identified in terms of the phi and the Tor function, because these are the two functions that we actually work with. And then finally a so-called Bootstrap argument, which then allows us to deduce this infrared bound. So what's a Bootstrap argument? So it's a Bootstrap argument somehow you can think of as, on the first glance, it's too good to be true. On the second glance, actually quite meaningful. So you make an assumption, and so the two quantities that we want to compare finally are this Fourier transform of the two-point function, the Tor head, and the Fourier transform of the Green's function. Yeah, and somehow we ideally want that these two are relatively close, and so we assume that they are already close. So this is already really good. Yeah, so let's say the ratio is at most 4, and then we use this bounds from step 2 to get bounds on pi, because somehow the pi's are bounded by the phi's and the tors, and so the phi's we know anyhow, but the tor, when we go to the Fourier transform, it's tor hat. We can then replace the tor hats by the g hats, and then we have a good control of this. And then we insert these in step 1. So step 1 was the expansion, so we put this in the expansion. And then we analyze the expansion identity and get that actually the tor hat over a g hat is not only smaller than 4, but it's even smaller than 3. Provided, say, that the dimension is large or this long-range parameter is large or something like that. This is a strategy in this third step. And then, well, I have not said for which lambda we do this, but this we do uniform in lambda in this whole subcritical regime, and uniform somehow in this in K. And then so then we kind of know that somehow tor hat and g hat are very close together, and then we kind of put in the well-known property g hat, and we are done. This is this final part of the argument. So in a way, so these 3 steps are kind of standard in all these expansion proofs. The first one, I would say, is the most interesting, because there you really have to, I mean, there's lots of novelty in that, and that's why I want to zoom in on that. The second one is the most complicated and most technical one, and the third one is a well-established theory by now. So let's kind of look at some aspects of this expansion. And it uses some special features of Poisson processes, in particular Poisson thinning. And this is what I want to explain next. So the goal is to find an identity of this point, in particular to get an expression for this pi's. So to this end, I've explained the notion of pivotality. So again, if 2 points x and y are connected, so that we have a picture similar to before, we have these 2 red points which we've added, and the black points which we've sampled as a Poisson point, and then we've also sampled these edges in between the black point, and then these new edges from the red points to the black points. And then you can have, for example, you could kind of end up with a realization such as this one. And this point in the middle here, this is what we call a pivotal point. Why is it pivotal? It is pivotal because if you would remove that point, then the connection between x and y would be broken. These are the pivotal points. And these pivotal points play an important role. So so the picture that you should have about so critical percolation configurations look different from supercritical ones, in the sense that if x and y are far away and they are connected, then the typical path from x to y, or typical realization, will have lots of these pivotal points. So somehow you go from this pivotal point to pivotal point, either via a direct edge or via like a double connection. There's next pivotal point, and next pivotal point, next pivotal point. And then we start the expansion. And so let me try to draw some of this. So let's say there is x and there is y, and they are connected, somehow connected. So let me draw, like this means somehow connected. Okay, so there are different possibilities. We have had them already. So one possibility is that we, can we have this straighter line like this? Yeah, much better. Either there's a direct edge between x and y, so that's a straight line, or there is such a double connection meaning there are 2 edge disjoint paths from x to y. So we start in x and y with 2 paths, one path and another path. That's a double connection. And the third thing is that they are connected, but neither of the 2 which we have already. So that means there is a double connection to some pivotal point, and that's the first pivotal point. And from there, we are connected to y. Yeah, so I make this in order to clarify that, of course, there are well, there's on the left-hand side, there's a sausage, and of course, these connected components can look rather complicated. But so this red line should indicate that this part of the cluster should not intersect with this. I mean, this cannot happen because then this point would not be pivotal. So this is the first pivotal point. For this connection from X to Y. Yeah. And so that's this was what we want to zoom in now. So we have this probability. Here we look at the probability of such an event occurring. So that's somehow on the left hand side is precisely this event which we were drawing before. So we go from X to Y, and there is somewhere a pivotal point, and it's also a first one in the sense that the one closest to X. That's in that sense it's closest in this realization. And so the first thing we want to do is we kind of want to make this pivotal point. We want to kind of hold in our hands in order to, in other words, to make this a point that we know where it is. And there is an identity from point process theory which is known to people in stochastic geometry, and I learned all of this. It's called Mecca identity, which allows you to at this point u. Yeah, so it's now a new process, where we not only add x, y, but we also add u, and then we integrate over the location of u, and we get that intensity of the Poisson process. That's one of these many tricks that you learn. And what we want to do then is a decoupling. So we have now a configuration where x is connected to u, and it's even doubly connected. And then u is connected to y, but somehow this part of the cluster is not interfering with this part of the cluster. Yeah? So this is kind of indicated with that red line. So this on the left side here we have this green part. So that's what I've been writing here. So x is connected to u, and then on the right hand side we have that u and y. We have this connection. But so ideally we would like to make this a product of two things. Yeah? We want to have this double connection from x to u, and then this single connection from u to y. But this is not quite true, because somehow we have this this property of being pivotal kind of requires more. And so here is where we really use point process theory and saying that, okay, we first explore the cluster of X without saying where U is. And then we add U and try to connect it to the points in X, and somehow, let's say, these two were successful. So that means we know everything on the left-hand side. So what happens then is that this connection from U to Y on the right side, it must not kind of have contact with the green cluster. So therefore, we have a reduced intensity, and the intensity somehow for each of the points in this cluster except U, we have that in this new intensity. So for the points that go from U to Y, we take 1 minus the probability that V is going to this point. You know, somehow saying, I mean, so we just have less points. And so this reduced intensity is the intensity which is left after somehow this we fix this cluster. You know, the green cluster is fixed, and then we have this on the right. For the rest of the connection, we have a reduced intensity. So now we redo this. I mean, now comes the inclusion X. We say, okay, well, that's not a good thing, or not an easy thing for us to deal with. So what instead we want is that this is just one. So we ignore this, but then we have too many points, and therefore we have to overcount the probability of this connection from U to Y, and we have to compensate for that. And that's where this inclusion exclusion gets going. So let me try to indicate the next step in the expansion only pictorially because that's maybe most informative here. So on the left-hand side, this is Tor, the fact that we have a connection between the 2 points. Then this was phi, the probability that we have a direct connection. Then there is a double connection, but not direct. So that is the first contribution to this quantity pi. So that will ultimately become an infinite sum of more and more complicated objects, but like the simplest and zeroth object in that one is this double connection. And then we have this quantity which we are discussing here. So what's that one? So we would like to have this as lambda for this point, and then we have here the connection of this first part times, and then we have a connection from u to y. So this one is Tor, and this is again pi 0. This is looking good. Yeah, if you remember what we're actually aiming to prove, because we are aiming to prove that Tor is equal to phi plus pi plus the convolution of pi and Tor. So that already goes in the right direction, except that it's not correct because, as I said, we are overcounting. So what are we overcounting? We have the double connection here, and then we have the this one. So now comes this Poisson thinning. So let's say this green cluster is like this. So so it's everything until here, and then there was this we wanted red, and then there is one. So there's one vertex here which belongs to the green cluster, and it is absorbing this cluster here, this point here, and somehow this is maybe it's absorbing another point here as well, because, well, of course, I said somehow there are lots of pivotal points. So there's this one guy, and he kind of removes, he makes that this connection is not anymore realized after somehow he's thinning this out, and he's doing this with precisely this probability. Yeah. Okay, so we have to subtract that, and then this one gives us an connections of this form. Sorry, it's green, and then there is so this one was going into here, and so let's give some names. So here was X, here was the point U, and there's maybe a new point V, and then we have that this one, this point V is connected to the final destination Y. Yeah, again, we do the same game again. We have these configurations, and we have this this configuration times the remaining connection, and then we say, okay, we factorize this minus the overcounting. And this one here is our contribution pi 1. And so this pi 0 and a pi 1, and then the further contributions, they will ultimately compose our pi. Yeah, so somehow you see here that we bound this coefficients pi via so-called diagrams. So diagrams are like small and standardized convolutions of tors and phis. And so here's this pi naught. Pi naught, we said, was a double connection, but not a direct connection. And this one we can bound above by the convolution of two tors. Namely, we start here, we go somewhere, and then we go back. And this is somewhere as u, so that is x, and that is u. And so that would be one of these bounds. Second, pi 1 is a little more complicated. So that was the picture which we were just drawing. So there's a connection to this point, and from here we have this, we have the thinning, and well, if we rearrange this, then it looks like that. Somehow you see that this picture is the same as this one. It's only that somehow this point is getting here, this point is going here. And well, it turns out somehow that this is just, well, it's just phi between these 2 points. Yeah, that's a probability that somehow you're thinning out this point. So we actually can treat this as if there was a connection. And then we use the BK inequality to put this into pieces, smaller pieces, like maybe one piece, this is one piece, and then there's one piece over here. And this way we bound it. Good. So time is more or less up. Let me give a summary of what has been achieved here. So we have derived the Slate's expansion proof in the continuum setup for the random connection model. This, the analysis of Slate's expansion obtains a trying condition, and it allows us to have a very good understanding of the critical behavior. And the whole proof is directly in the continuum, so it does not proceed via discretization. So in the past, people said, be wise, discretize, and somehow I feel proud not to be wise, but to not discretize, but somehow to really use this point process theory here. The challenge, challenges or things for further work would be to do this on a finite domain, in particular on tori, and that would kind of open up the road to this random geometric graphs. There are somehow two schools. The people with training in statistical physics often think of finite domains as doing the same system, but somehow on a finite box and making the box larger and larger and larger. And people that come from random graphs and study random geometric graphs, they often think of like the unit cube with, say, periodic boundary conditions, and then putting more and more boxes inside this unit cube, but somehow then adjust the connection probability inside the box as more points go into the box. This is the two are equivalent, of course, but somehow they are two different traditions in how to deal with that. And the previous model was on an infinite domain, but somehow there are techniques to do that in finite domain, but that has not been done. Of course, an obvious question is can we do this for other point processes which are not Poisson? And I don't know. I would guess that this should be true in much more generality. But our proof uses heavily the fact that we have Poisson. So now it's really, all this Poisson thinning, that would completely break down when we have not Poisson anymore. So I would guess the result is true, but I would not currently, as you know, a way to prove this. And then the third thing is to make the connection with the previous talk and do these things with weights. The weights were absent now. Can we do this with weights? This is something we actively work on, and we might, I don't know, maybe at some point I can report on that as well. Thank you very much.
Thank you very much, Markus, for this beautiful and very instructive talk. Are there questions or comments?
Sorry, you have started the proof from some assumptions that some ratio is less than 4. But what happens then with this assumption?
I draw a picture. It's so let's say here's lambda, and here is this ratio tau head of k over g head of k. And then I said somehow, okay, let's suppose maybe here's 4. Let's suppose we're smaller than 4. Then we are also smaller than, say, 3. Yeah? So that means that somehow there's nothing in between here. And then additionally, there's some, I did not say anything, but as you rightfully point out. So additionally, you want to make sure that for, say, lambda equal to 0 or some small lambda, it is below 3. And the function is continuous in lambda. And then you know, well, from the intermediate value theorem of continuous functions, that it must be smaller than 3 for all lambda.
And how to use this fact?
At some point, yes, lambda c. So everything is until here. So, but it is, you know, somehow that for all the lambdas, this ratio is smaller than 3, and you know this one very well. And so this is basically the so g hat of k. This is something of the form phi hat of 0 minus phi hat of k. Yeah? So that's coming out of the g hat. So something, so the numerator is not right, but the denominator, that's the main thing. So it's diverging at k, but so you know precisely how it diverges at k. And this gives you the uniform bound for lambda small, lambda c, and then when you derive the trying condition, you derive it somehow, you get this bound uniformly for lambda small, lambda c, and then you can use some limit argument to get it for lambda c as well.
Thank you.
Further questions or comments?
Yes, I have one. Would it be of any help to prove directly the Ornstein-Zernicke behavior for the subcritical two-point function instead of going through the lace expansion? Like it has been done, for example, in subcritical bond percolation.
It's, I guess, not, because somehow the main, well, there's one thing which confused me at least, and that is there's an Ornstein-Zernicke equation and an Ornstein-Zernicke decay, and the two have the same name, but when they're used somehow differently here. The main thing here, and that's the main thing with this particular expansion. I mean, there are different ways to prove that there is such an expansion, but the lace expansion, as we've done it here, has the main advantage that all the terms are convergent until the critical point. Often, I mean, there is this 1 over the integral of phi. So that's basically the branching process critical point, which would appear if you have branching random walks or like a continuum version of that. So normally you have no problems with proving convergence until this point. So this one is fine, but this is a problematic region. So you need somehow to set up your expansion in a way that all your quantities are convergent or uniformly convergent until the critical point, all the way until here. And this is so I don't. Cannot give a totally finite answer to a question, but I would be skeptical because of this. That's my experience.
Thank you.
So if there are no further questions, I suggest that we unmute ourselves to give Markus an applause. And I will stop the recording, but leave the meeting open for a moment.